So I want to give you a little bit more feel for how you prove that languages are not regular. And let's start by talking about proof by contradiction, okay? Because this all depends on understanding proof by contradiction. So suppose we're in the classroom, and let's just draw a picture of our classroom. Here's our classroom. And my classroom happens to have two windows. Maybe my classroom is a very strange classroom that's a box. And there's one window, and there's the other window. Maybe the building continues on out here. Anyway, let's suppose that I want to write a proof. So let's move this a little bit out of the way. There's my classroom. And let's suppose I want to prove that it is raining outside. Oops, come on. There we go. So I want to prove that it is raining, okay? And you know what? I'm going to do this proof a little bit of a weird way. Of course, I'm doing it a weird way because I'm using proof by contradiction, but stick with me and let's see what happens, okay? So I want to prove that it's raining. And for some strange reason, which will become obvious as time goes on, I'm going to assume it is not raining. So I'm going to assume it's not raining. And having made this assumption that it's not raining, I make some observations. And maybe I see, you know, a bunch of people carrying umbrellas. It's supposed to look like an umbrella. And I say, okay, fine. Well, I see people carrying umbrellas, but maybe that's because it's Umbrella Appreciation Day and people get prizes for carrying umbrellas or for being found carrying an umbrella. So I can kind of discount that. And I can say, all right, well, that's still consistent with my original assumption. I can still assume it's not raining. And then I notice that those umbrellas are kind of wet, right? So they're kind of dripping. And I say, well, yeah, that's fine, but that's still consistent with my assumption that it's not raining because, you know, it's possible, maybe it's not likely, but it's completely possible that there's somebody outside who has a hose. And, you know, here's, we're getting to about the limit of my drawing ability, but they have a hose, and that hose is spraying water. And so, you know, it's plausible there's a hose, the hose is spraying water, the people are getting wet. And also the umbrellas are getting wet and they're dripping. And I go through a bunch of steps like this and I say, people are wearing raincoats. Yeah, well, you know, maybe raincoats are fashionable right now. Who knows? I'm not always the person up on fashion the most. But then at some point, maybe I get an email from the Rowan announcer and they say, oh, there is no water on campus. The water is all broken and no water is going to come out of any pipe anywhere on campus for the rest of the day, and there is just no way to get water onto campus artificially. And at that point, I coincidentally happened to stick my hand out the window. All right, I have a big hand for a small window, but anyway, and my hand starts getting wet. And I think, hang on a minute, my hand is getting wet, right? I could argue away that all these people who have, you know, the wet umbrellas and all this good stuff, that happened before the water went out. But now the water is out. I know the water is out. I'm sure the water is out. I stick my hand out and it gets wet. And now I've got this dilemma. There is absolutely no way, and trust me, let's just assume that there is no way my hand can get wet at this point if it's not raining. But my hand is wet. But I've assumed it's not raining. But my hand is wet. But I assumed it's not raining. And if my hand is wet, that's it. Forget it. There's no, my hand is wet. I know my hand is wet. So I guess what I assumed to be the case was not the case. In fact, my assumption that it is not raining must be false. And if my assumption that it's not raining is false, that means that I have proven that it's raining. Now, I understand that this is a bit of a stretch, and this is a little bit of a silly example, but I want you to kind of get the feel for what we're trying to use the pumping lemma for. So the idea with the pumping lemma is that we know that if you have a language that is regular, so let's say I have a language L, and the important thing is that the language L is regular. So this is what the pumping lemma is about. Not how we use the pumping lemma to prove that languages are not regular, but just the fact that the pumping lemma says if you have a language L and L is regular, then there is some number M. Now, it doesn't tell us what the M is. We saw before that it has to do with the size of the DFA, the number of states on the DFA. But strictly speaking, there is some number M for which any string that you pick that is at least as long as M. So if you have a string S, which is in my language, and the length of S is greater than or equal to M, then S can be split up into three pieces, X, Y, Z. So when we concatenate X, Y, and Z together, we have exactly S, right? And this split that happens, one of the important facts that you know about this split is that the length of the XY piece is no longer than M. It can be M characters or fewer. And we also know that the Y piece has to have something in it. So the Y piece is, the length of the Y piece, the size of the Y piece is greater than 0. And given all these facts, it is also the case that any string x, y to the n, z, such that n is a natural number, right? All these strings are in my language. Okay, so let's just look at this again. This is what the pumping lemma says. The pumping lemma says, if you have a language called L and your language is regular, then there is some number M where if you have any strings in L whose length is greater than or equal to M, you can split it into this XYZ part. The XY part, when you just count the letters in the XY part, there's no more than M, less than or equal to M. The Y part has something in it, it's not 0, and all of these strings with 0 or more Y's in them are in my language. Now, here's the interesting thing. This pumping lemma is not telling us anything about languages that are not regular. It's not telling us how to prove that languages are not regular. It's just telling us something that is true about regular languages. So the way we do our proofs to show that a language is not regular is we follow the following steps, okay? Step 1, we assume it's regular, right? We assume our language is regular. And if the language is regular, then we know the stuff that the pumping lemma says is true, because the pumping lemma says if your language is regular, in fact, maybe we should write if L is regular, then there exists, that backwards upside down E means there exists. So there exists some M such that for any string greater than L whose length is greater than or equal to M, you can look at the official version of the pumping lemma in the book, right? But if we assume it's regular, the pumping lemma is true, right? So what we're going to do to prove that it's not regular is we're going to assume it's regular, and then we're going to do the rain trick, right? We're going to assume it's regular. We're going to do a bunch of steps that say, well, let me pick a special string and let me make sure the string meets these criteria that the pumping lemma has. And we're going to do more stuff, and we're going to show that some string that we generate from this XYZ part, right, is not in my language. Okay? And so we're going to show that maybe x, y, y, z is not in the language. Or maybe we're going to show that xz is not in the language, right? Or maybe something else, but we're going to do something like this. And that gives us a giant contradiction, right? Because on the one hand, if it's regular, then everything the pumping lemma says must be true. But we've found something that the pumping lemma said that was not true. But if it's regular, the pumping lemma is true. But what we found says it's not true. Therefore, we have a contradiction, and our assumption, which was that the language was regular, must not be correct. Okay? So you can look back at the first proof we did in the other videos to show that the language a to the n, b to the n is not regular. Right, so I'm not going to rewrite that again. I'm just going to say go watch other video proof showing that the language a to the n, b to the n, such that n is in the natural numbers, is not regular. Okay, pause this video now. Go watch that other video. Okay, you should have watched it already. Go watch it again. After you are done watching it, come back here and keep going. Okay, so I'm assuming you watched the video. The big trick in all of these proofs that a language is not regular has to do with how you pick your string. Okay, so you get to pick one string. Remember that if you can find any string, right, the pumping lemma says every string can be pumped, right, can have its y's changed, right? So the pumping lemma says any string s whose length is at least m characters long, right, can be pumped. Right? And by pumped, I just mean you're either adding y's to it or getting rid of the y, right? But any string can be pumped. So we just have to pick a clever string. And then if we pick the right string, we can pick one that we intentionally mess up. Now, remember that what you're doing with this is this is a lot of work that happens behind the scenes. Whenever you see me do one of these proofs or you see anybody doing one of these proofs, what you see is something really beautiful, right? You see something that looks a lot like this outline that you can find, by the way, in the other materials from class on our homepage, where someone has taken this outline and they have filled in all this stuff, and the string that they pick in particular, they've just come up with some magic string and they say something about the structure of the language, and it all looks beautiful and you get this proof, okay? But behind the scenes, people have been thinking about how do I pick a string so that I can break this, right? So what I want to talk about is how you pick strings that break this. So let's start by looking at the string that we picked in that first example. So the string that we picked in the example where we're trying to prove that a to the n, b to the n, such that n is in n is not regular, right? The string that we picked in here is the string a to the m, b to the m, okay? And why did we pick this? Well, we have to pick a string where the length of my string is greater than or equal to m. And if you look at this string here, a to the m, b to the m, definitely longer than m, right? Its length is actually 2m, so we're good. And the other thing that you want to do, and this is kind of the art and the tricky part of this, is you want to pick a string where you know something about y. You know something about what y looks like, right? And to do that, usually we're taking advantage of the fact that the pumping lemma says that the length of the xy piece is less than or equal to m. So in the case of this a to the m, b to the m string that I picked, I know for sure, no question, that the first m letters in the string are all a's. I don't know what the heck m is, but I say let m be the number from the pumping lemma, and I know the first m letters are a's, and I know that both the x and y parts have to happen in the first m letters. And I also know that the y part, right, the length of the y part has to be greater than or equal to 1. It can't be empty, right? And if I look at my first m letters, those are all a's. So in this example, I took this trick where I said, well, y is all a's, right? And if I do the pumping trick where I take like x, y, y, z, and I look at that string, which should be in my language, I know I'm adding a's. And remember, my language has to have the same number of a's as b's, right? It's a to the n, b to the n. So if I end up with, a to the m plus something, right? In the proof, I think we used letter k. If I have more a's than b's, it's not in my language. And then I get to say, wait a minute, pumping lemma says if it's regular, it has to be in my language. I guarantee it's not in my language. Therefore, my language must not be regular. Okay? So what I want to do in the rest of this video is just look at some other problems and talk about how to pick a good string so that your y the y messes things up. So let's consider this language. Let's show that this language, the set of all palindromes over the alphabet A, B of odd length, are not regular. Okay, so I want to prove that the language L, all palindromes over the language. So the language L equals this is not regular. Okay. I want to prove this. And I get to pick one string, right? And I'm trying to think, well, first off, what's a palindrome, right? So just to review, palindrome is a string where it looks the same if you start at the front or the back. So if I do like A, B, A, that's a palindrome, or A, B, B, A, B, B, A, that's another palindrome, right? Because if I read it this way or this way, it's the same. AA is a palindrome, though that's a palindrome of even length, right? So we're talking about palindromes of odd length, okay? And what I need to do is I need to say, well, it has to be at least m characters long, right? So my first criteria is I need to make sure it's at least m characters long. And I also want to pick a string that, pumping will mess it up, right? So the question is, how do I do this? And my first thought is with every single string that I try to do on the pumping lemma, my first thought is, can I start with something like A to the M? Because that is definitely m letters long, right? Now I don't know if A to the M is odd or even, right, of odd or even length. So I could say, A to the M, A to the M, well, that's definitely of odd length, right? But if I add more A's to this, it's still going to be a palindrome, so that doesn't really help me much. So I guess I need something that's going to mess up, right? And it may not be obvious. It may take a little time. You have to see a few examples of this to get it. But, what about A to the M, B, A to the M? Well, that is definitely in my language, right? That's a palindrome over AB of odd length. And the interesting thing here is because I have the A to the M at the beginning, I know for sure that y is going to be all a's. Right? So what's going to happen if I have x, y, y, z? Well, if I have x, y, y, z, and y is all a's, so now I say, you know, let's suppose y is a to the k for some k, and I know for a fact that k is greater than or equal to 1, and it is less than or equal to m, right? Right? But so that means that x, y, y, z, right? If I do the math through, what I find is that x, y, y, z is equal to a to the m plus k, b a to the m, and I say, wait, that's not in my language, right? In terms of doing the proof, so now I've done my scratch work, right? In terms of doing the proof, I have to go and do the whole thing again. So let me go and get that outline, and we'll do it on the outline. All right, so here is how we're going to prove this, okay? Here's a statement I want to prove, so let's cross out this fill in the blank, and we're going to write the thing that I want to prove is that the set of all palindromes over the alphabet A, B, that should say all odd palindromes over the alphabet A, B, is not a regular language. Proof. Well, let L equal the set of all odd palindromes over the alphabet AB. Assume L is regular. Let M be the number from the pumping lemma. Let S equal, and we're going to put in up here, we're going to put A to the M, B, A to the M. Since S is in my language, yes it is, right? Because that's a palindrome of odd length. And the length of S is greater than or equal to M because the length of S actually equals 2M plus 1, right? The pumping lemma must apply. Specifically, S can be split up into x, y, z, where y is not lambda and the nth of x, y is less than m. And now I get to say y must be all a's and so y takes the form a to the k, where k is greater than or equal to 1 and less than or equal to m, right? By the pumping lemma, x, y, y, z is in the language. What is x, y, y, z? Well, and you should do the math out a little bit more so that you show me how you got this. Let me just, but I'm just going to say, well, x, y, y, z is a to the m plus k, b a to the m, where k is greater than 0. So x, y, y, z is not in the language, right? And now we say, wait a minute, x, y, y, z isn't in the language, but it is, but it isn't, but it is, but it isn't, but it is. So we have a contradiction. Thus, our assumption must not be true. What was our assumption? Our assumption way up at the top of the page was we assumed L was regular. We now know our assumption is not true. Thus, L must not be regular, QED, end of proof. Okay, So suppose we're looking at this language, the language a to the n, b to the f, such that n and f are both natural numbers, and also n is less than or equal to f. Okay? We want to prove that that's not regular. Okay? So again, this is the background work. I'm going to need to pick a string. I know I'm going to have to pick a string. I get to pick one, and I want to pick one that somehow makes it easiest for me to figure out what y is. So I'm going to pick the string a to the m, and then I got to figure out what to pick for b. Well, the n part has to be less than the f part, right? There's to be fewer a's than b's, or the same number. And I'm going to start by just saying b to the m and see if that works. Because really, I'm sort of thinking ahead, and I'm thinking, well, if I pick the string a to the m, b to the m, then what's going to happen is my y is going to be all a's, right? And I'm going to add an a or two on this side, but that will mean that instead of taking this form where I have, fewer a's than b's, suddenly I will have more a's than b's, and that's not in my language, right? So let's see how that proof works. So here's what I want to prove. I want to prove that the language a to the n, b to the f, such that n and f are natural numbers, and n is less than or equal to f, is not a regular language. Here's my proof. Let L equal a to the n, b to the f, such that n and f are in my natural language, and n is less than or equal to f, right? Assume L is regular. Let m be the number from the pumping lemma. Let S equal, well, I picked my special string. I'm going to pick the special string a to the m, b to the m. Now I need to verify. S is in my language, right? Yep, S is in my language. The length of S is at least m. Yep, S is 2m. The length of S is 2m, right? Specifically, so the pumping lemma must apply, specifically all this good stuff, right? X can be split into x, y, z, where y isn't empty, and the length of the x, y part is less than or equal to m. So since the length of the x, y part is less than or equal to m, y must be all a's. Let y equal a to the k, and again, we know that k is greater than or equal to 1 and less than or equal to m, right? By the pumping lemma, well, we know by the pumping lemma that x, y, y, z should be in my language, right? Is an element of language. What is x, y, y, z? Well, x, y, y, z equals, and how many a's are there now? There's the m you already have plus the extra k you stuffed in. So a to the m plus k, b to the m, right? Which is not in my language because m plus k is greater than m, right? So that gives me a contradiction. Thus, our assumption must not be true. Remember, what was my assumption? My assumption was that L is regular, but my assumption must not be true. Thus, L must not be regular, QED. So let's consider this kind of weird language here for a minute. This language is the language of all strings that take the form 3a's, followed by some number of b's, followed by, well, I guess we have to change this slightly. N is an element of n, and n is greater than or equal to 3. So we have the same number of c's as we do a's and b's. So For example, here's a couple of strings in that language, A, B, and then 4 C's, right? So N is 4 in this case, or A, followed by 1, 2, 3 B's, and 1, 2, 3, 4, 5, 6 C's, or even A with no B's and C, right? So those are all strings in my language. And now I have this big problem because I don't know how big M is. And M might be, if I'm lucky, M might be 3, but M might be bigger than 3. So I need to limit my choice as much as possible so that I can tell you what Y looks like, so that I can mess up this system, right? And so what I'm going to do is I'm going to pick this string. I'm going to say A to the 3, B to the M minus 3, C to the M. Okay? Now that's definitely in my language. That is definitely at least M letters long, right? That's actually 2 M letters long again, I think, right? So the length of this string is 2M, right? And if I take this string and I say, what is Y? Well, Y has to happen in the first M characters. What are my first M characters? It's these guys. So now I've got 3 choices for Y. Y could be all A's, or some A's, you know, at most 3, and some B's, or it could be all B's. And the trick with the proof that this string, that this language is not regular, is you have to say, well, okay, let me assume it's regular, and I pick this string here, right? And then I say, okay, well, if I have this string, then Y could be, well, case 1, all A's, case 2, some A's and B's, case 3, all B's. If any of these 3 can be pumped, then I need to pick a different string, because the whole idea is to show this string, no matter what I do, cannot be pumped, right? How do I show this string can't be pumped? I say, well, this string, Y has to be either all A's, or some A's and some B's, or all B's. And look, when it's all A's, can't be pumped. And look, when it's all some A's and some B's, can't be pumped. And look, when it's all B's, it can't be pumped. So no matter how I try, this string cannot be pumped. Therefore, I get my contradiction. So let's look at that. So let's take a look at how the proof's going to go. We're going to have 3 cases, and we're going to say case 1. Suppose that Y is all A's. Now, in this case, we know that Y can only be one of 3 things if it's all A's, right? Y could be the string A, it could be the string AA, or it could be the string AAA, because we only have 3 A's. But that's okay, I don't care about that. What I care about is that Y is all A's. And so I can say, let's suppose Y is A to the K, you know, for some K which is greater than or equal to 1 and less than or equal to, not less than or equal to M in this case. It's actually less than or equal to 3, right? So if Y is this A to the K, then X, Y, Y, Z is still going to equal A to the 3 plus K, B to the M minus 3, C to the M, which is not in my language, right? But that's just the case 1. This doesn't tell me my language isn't regular yet. It just tells me, I guess Y isn't all A's, right? So Y is not all A's. Okay, so we know that the Y happens in the first M characters and it's not all A's, But maybe we have case 2, where y takes the form some a's and some b's. I don't know, b to the q. And we know that k is going to be between 1 and 3, and q is going to be between 1. We have to have a b, otherwise y wouldn't be of this form, right? Between 1 and how many b's are there? m minus 3, right? So this is a little trickier to see. So let's see what we've got here. Y has some a's and b's. So if we think about this, x is 0 or more a's. I guess x really has to be 0 or 1 or 2 a's, right? Because y gets the rest. And y has our a to the k, b to the q. And what's z? Well, z has, how many b's does it have? It has whatever we had, m minus 3 minus the q a's that are in y already. So z is going to equal b to the m minus 3 minus q, c to the m. So what is x, y, y, z? Well, the x, y part, the first bit, I know for sure has all the a's, and then it has QB's, right? Because we go through some of the A's, we go through some of the B's, which means that we definitely get those first 3 A's in there between X and Y. So I don't know about Y, how many are in Y and how many are in X, but I know between X and Y we got all the A's. And then because this is what I said Y equals this thing, I know I've got QB's in Y. And then I want another Y, right? So let's copy that again. So I have another a to the k, b to the q, where k isn't 0, right? K is between 1 and 3. So that's my second y. And then I have z, and we said z was b to the m minus 3 minus q, c to the m. And if we look at this string, you can see now we've got some A's, some B's, some more A's and some more B's, and then some C's, and that is not in my language, right? My language said 3 A's, then some B's, then some C's. So this is not in my language, right? So clearly, Y does not consist of some A's and some B's. So we're in last chance territory now here, right? Case 3, which is Y is all B's. And you know, if you're still holding out hope, maybe this language is regular, then, you know, Y has to be all B's because we showed it couldn't be all A's, couldn't be some A's and B's, but maybe, just maybe it could be all B's, right? So now what I'm going to do is say, okay, well, if Y is all B's, then Y takes the form B to the K, right, where K has to be greater than or equal to 1 because Y can't be empty, and it's less than or equal to m minus 3, right? So what is x? Well, x is going to equal all the a's and then some number of b's. I don't know, maybe we have b to the g, where I guess g has to be greater than or equal to 0. There might be no b's in x, right? X might just be all a's, or it could also be, I guess, less than or equal to m minus 4, because we have to save at least one of those b's for y. And z is the rest of the b's. So I guess z is going to equal b to the m minus 3, and then we get rid of the ones that are in y, and we get rid of the ones that are in x. So it's all the rest, followed by MCs. So what is x, y, y, z? Well, let's see. We get a to the 3, b to the g. That's the x part. The y part is b to the k. The y part, we'll do it twice, is b to the k, right? Because we're doing x, y, y, z. And z is b to the m minus 3 minus k minus g, c to the m. And now we look and we see, well, all these b's, right? They're b's in a row. So I have gb's and kb's and kb's, da, da, da. And if I simplify the math, what I find is I end up with a to the 3. And let's see, this g cancels out that one, right? Because we have gb's in a row here, but we have negative gb's here, and that k crosses out with that piece. And so what we end up with is a to the 3, b to the m minus 3 plus k, c to the m. And again, that's not in my language. All right. So now let's look at the big proof. Okay, here we go. Suppose I want to prove that a to the 3, b to the n minus 3, c to the n such that n is an element of n, and n is greater than or equal to 3, is not a regular language. Proof. Let L equal the language a to the 3, b to the n minus 3, c to the n such that n is natural number and n is greater than or equal to 3, right? Assume L is regular. Let M be the number from the pumping lemma. Let S be a to the 3, b to the m minus 3, c to the m. Since S is an element of L and the size of S is greater or equal to m, right, how big is S? Well, again, it looks like the length of S is 2m here, right? Because I have 3 plus m minus 3 plus m letters. The pumping lemma must apply. Specifically, S takes the form x, y, z, where we know y is not empty, and we know that the x and y part happen within the first m letters. Now we need to say something about the structure of y. Well, this is where we say the interesting stuff, where we say y is either all A's, some A's and B's, or all B's. And now I say, by the pumping lemma, right, X, Y, Y, Z is in my language. And then what I have to do is I have to do all the cases. Case 1, suppose Y is all A's. And then I go through the stuff I showed you on the previous page. Case 2, da-da-da. Case 3, da-da-da. And I say, wait, Y has to be all A's or some A's and some B's, or all B's, let's get a little bit more space, but no matter what Y looks like, X, Y, Y, Z is not in my language. But hang on again. We said X, Y, Y, Z must be in my language, but it's not in my language. But it must be in my language, but it's not in my language. So now we get to write this contradiction part. Thus, our assumption must be not be true. Thus, L must not be regular. QED. So just to summarize, you get to pick the string you want to mess with, right? And you want to pick the string ideally so that y is just one letter. So if you can make y be just one letter, that's great. Right? You may not be able to do that, but whatever you do, you need to think about what is the form of y, what happens if I look at x, y, y, z, or what happens if I look at x, z, right? And can I show that one of these two is not in the language? Or maybe x with 3 y's. I mean, you may have to go for 3. You may have to go for 27 y's. I hope not. But you want to show that one of these things is not in the language. And if it's not in the language, and the pumping lemma says it has to be in the language if it's regular, then it's not regular.